Hello, welcome to this presentation, Cross-Validation for Multiple Methods of Synthetic Data Generation. My name is Lin Guo. I'm Assistant Professor in Industrial Engineering at South Dakota School of Mines and Technology. This work is co-authored by Nathan Press, a senior student in computer science, Professor Jenny Talon and Professor Fire Chemistry. They're all from University of Oklahoma. This work in progress paper is the outcome of an undergraduate research project done by Nathan. So let's look at the motivation. The problem is when seeking treatment, patients may be subject to bottlenecks. This results in long waiting times and patient dissatisfaction, and also worsening their health condition. And to identify bottlenecks, we need to curate data because we do not have sufficient real data in the right format. So we look at the methods used in literature regarding hospital efficiency. There are 3 clusters: agent-based models, network flow models, and other types. By critically reviewing the literature, we identify some gaps and limitations. So here we pose 3 research questions for our project. We'll fill the gaps by answering the questions. First, how do we detect bottlenecks of a patient flow network model using the data from other types of model? Second, how can we improve the network flow efficiency by reallocating current resource? Third, how can we verify the result of reallocating resource? So we propose a cross-validation methods for multiple methods to answer the questions. We extract the data from a first type of model, based on which we build another type of model, using which we may identify how to improve a process more easily. We name it improvement action A. By taking action A, we modify the model type 2 and get the result, based on which we modify model type 1. And then we compare the baseline type 1 model and the modified type 1 model. If the modified model works better, we accept the action A. If not, we reject it. In our project, we choose agent-based model as type 1 model, from which we get patients' flow data. Using this data, we build a network flow model. By analyzing the network flow model, we can identify the bottleneck and remove it by changing the topology, which result in new clinic procedure. Then we modify the agent-based model based on the new procedure, comparing the baseline model with the modified model, so we can make a decision on whether to accept the topology change. The network flow model is based on the agent-based model from Bobby's 2017 paper. The other model, the Orlando Veteran Affairs Medical Center, VAMC for short. We select a small part of the model as a sample to test our proposed method. In the network model, we define each node as a station that a patient receives certain care or test or treatment or paperwork, etc. Unlike an agent-based model that tracks individual patients as they move through a primary care clinic, a network flow model tracks how patients move through a network with capacitated edges that connect various nodes, presenting various procedures. When a node's flow in is greater than its flow out in a period, we define it as a bottleneck. Then, if there are several bottlenecks in a network, we deal with the worst one first, or we deal with the one that we can deal with our current knowledge. We define the efficiency of a node as its flow out divided by flow in a period. We define the total wait time as this: within a period, time per patient being treated minus time per patient being flowed in, multiplied by the number of patients flow in minus 1. If in a period the patients being treated are more than the patients flowed in, then we define that the flow runs smooth. No patients needs to wait. In this case, total wait time is 0. We define individual wait time as a function consisted of the number of patients in queue and the rate at which they are being served. The maximum single patient wait time is the longest possible wait time in the network, and it's the worst case. We want to minimize it. And we assume patient's arrival is equally interspersed in a time interval, because the time interval is very short, just 1 minute. Given the definitions, we generate more data from our network flow model. Here are the nodes of our model. Here's the data. We get theoretical patients per day from the Orlando VAMC model, which is our type 1 model. And we use Poisson distribution to add stochasticity to each node, which reflects the randomness and uncertainty in a clinic. And this is the Ensemble run we use in this paper. For example, the probability of having 40 residents in a period is 6.3%. For a patient at the nurse node, the chance that she or he goes to a primary care physician is 24%, whereas she or he goes to reside in a hospital is 76%. After 500 Ensemble runs, we get patient's flow data. We get a mean and extreme case, or in other words, the worst case of the 500 runs. The efficiency here is the average of all nodes in the network. That is the average value of each node's flow out divided by its flow in, not the whole network's flow out over flow in. The unit of wait time is minute, and the time period is 8 hours. The time interval is minute. Suppose we don't have domain expertise on clinic efficiency, which we actually do not in this project. Instead of removing the bottleneck at the resident node, which may require or contribute to structural improvement of the operation efficiency here. Instead of that, we intuitively try to remove the bottleneck of the checkout node by changing the topology, which is adding a direct edge from primary care physician to the end. Let's test what difference this topology change will bring. If we plot the efficiency histogram of the baseline network model and the modified model is the one with changed topology. Then the horizontal axis represent the efficiency of the network. The higher, the better. And the vertical axis represent the count of the 500 runs. In the baseline model, which is on the left, 221 out of 500 runs are with 100% efficiency. And in the modified model, which is on the right, there are 270 runs with 100% efficiency. So we improve the efficiency by adding the edge. Then we look at the patient wait time. The horizontal axis show the longest single patient wait time. Here is 200 minutes for the baseline model. And here is the 200 minutes for the modified model. So, and the vertical axis represent the total wait time, also in minute. And here is the line of 3,000 minutes. So we also reduce the total wait time by modifying the model. In addition, we also increase the correlation between the longest single patient wait time and the total wait time. The R-square is improved here. So what is the benefit of having a higher correlation between the two? When the correlation between the two measures of wait time is high, we can analyze and improve the network efficiency by only dealing with one of them. This can help us reduce the number of objective functions of the model. And in this way, we can make sure that when we reduce the total wait time, most of the patients can benefit from it. So far, we can answer the 3 research questions we posed earlier. First, how do we detect the bottlenecks of a patient network flow model using the data from other types of model? So we use the patient flow data in the agent-based model to build a network flow model, use ensemble runs of the network flow model to account for uncertainty in the synthetic data. Second, how can we improve the network flow efficiency by reallocating current resource? The answer is by changing the topology of the network flow model. Bottlenecks are removed, increasing efficiency in the model and decreasing patient wait times. And third, How can we verify the result? Using multiple model types, we can verify whether a justification or modification action can bring a better result. However, what I have presented is only a part of the this map, this picture, the one in the round rectangle. We haven't just justified the agent-based model and compare the results. To finish testifying the proposed method, we need to do the rest work. That's our future work. Besides, in our future work, we can reduce the structural wait time, that is the bottleneck here in the resident node. Domain expertise is needed. And if we model the details inside this node, this will be another network, and we can use the same method to improve the network flow efficiency by modifying the topology of this subnetwork. And we can expand the method to a broader healthcare network, such as the hospital network, hospital or healthcare supply chain or supply network, and health plan network. We can also use more types of models and more types of data to improve a process in different ways and verify each other. And thank you for listening. We are looking forward to collaborations.